years, and he's also a president and CEO of renewables company. Uh, we'll stop at that and want to hear press what he wants to say. Okay, so I would request two things. One, please keep your mic on mute, and secondly, if you have any questions, you can type them in the chat box, and we'll take them up as we go along. Okay, over to you, Caps.
Okay, thanks. Thank you. So let me share this. Okay, just give me a thumbs up if you can see the screen. Somebody give me a thumbs up if you can see the screen. Okay,
Yes,
good.
we can. Yes,
Okay,
we can.
thanks. Thanks, good. Okay, so basically, when I was asked to put together something on the oil and gas industry, I looked at it from two very big sort of perspectives, at least two perspectives. So one is very generically, where does oil and gas fit in the current, in our world today, which is its impact on well-being of people and economic growth of different societies, countries, entities, whatever. And the second big sort of perspective could be more of the technical aspects of oil and gas, which is um, starting with petroleum geology, where is oil found, what kinds of reservoirs are there, upstream, which is production, exploration and production, then midstream, which is transport, downstream, which is refining, and then following refining, petrochemicals. And sort of more of a, I would say, engineer's perspective on oil and gas production and processing all the way through to.
मेरा वीडियो ऑफ कर मेरा मेरा वॉल्यूम.
So basically, these are the two approaches, and they are kind of different, sort of very different approaches. So what I would propose is, let's talk. I'll probably try to lead the discussion more on where is oil and gas, and does it have a future in the next 30, 50, 100 years or whatever, and how do we all see or perceive oil and gas as one of the energy sources compared to clean energy sources, concepts of renewables. There's renewable fuels, and then there's several other kinds of renewables. And very briefly, I'll try to share my perspective here. So usually when we look at sources of energy, at the lowest tier is biomass. And biomass essentially, for all practical purposes, is burning wood. Wood and woody plants. There's a very tiny, minuscule component of what we call burning cow dung, but that's a minuscule component given the grand scheme of things. So biomass is the lowest. Then comes coal, which has a fairly substantial role today in energy production. About a third, 25 to 30% of the energy is produced by coal. And then comes oil and gas, and oil and gas are treated differently for several reasons. One has to do with calorific value per unit of volume or mass. And the second has to do with ease of moving, transporting, compressing, handling, and risks. So gas is inherently more risky to transport and distribute than oil. So these are the three sort of big fossil fuel components, or so coal, oil, and natural gas. And so for the purposes of the rest of the discussion, I'm not going to address coal except to say how it compares with oil and gas and with some renewable fuels. Fair? Okay. So broadly wanted to talk about energy, global energy demand. We conflate energy with petroleum, which is not right. I mean, energy can come from many other sources, notably coal, also hydroelectric, nuclear power, and then increasingly renewables. So today renewables is about 2% of the energy production globally. Then a little bit about petroleum production, who are the main producers, where OPEC is the biggest cartel. Everybody is curious about commodity pricing, and the reality is we really don't have a very good understanding of how those markets move. At least I don't. Then progress a little bit to petroleum products, first within sort of what is considered the oil and gas industry, and then beyond, which is petrochemicals. Contribution to greenhouse gases, or aka GHG, or climate change, and then a little bit about energy transition. Is it going to happen? At what pace is it happening? Where do you think, if who was that smart man who made a comment that making predictions, especially about the future, is very difficult? But I will try to share what I think. Okay, and the rest of it I think are more on the technical side, and yes, there's some meandering there, talking about production, but also talking about some more about transition, carbon capture and sequestration, and hydrogen. And we are going to have a talk. I learned a few minutes ago, probably 2-3 months down the line, early in the new year, we are going to have a talk on the different shades of hydrogen. So this is where we are. Okay. So let me carry on with sort of starting with the global perspective. Um, I'm on camera. Sorry for that. Okay, so hang on, guys. Okay, so impact of not only energy but basically application of science and technology. I mean, this is sort of a concept of human well-being. You see a big spike for Bangladesh around 1971 for very good historical reasons, but in general, almost all countries, areas, even regions here like Asia and Africa are sort of summarized. But this is both developed and developing countries are showing very similar trends. And arguably, well-being of human beings has come from applying science, knowledge, and technology. And the more stable geopolitics is, and the more stable energy usage or access to energy is how economies have grown and sort of mankind has benefited as a whole. So quasi-stable geopolitics means we don't have world wars, we don't have things that set back humanity by decades. And energy usage, there's a sort of a very simple perspective or general rule of thumb, except for the really, and this is a normative comment, hunter-gatherer societies that don't really use, don't really have a structured, organized way of energy consumption. I mean, other than those societies, almost everywhere else in the last 100, 200 years, there's a very straight correlation, which is the increase in energy usage in any community, state, country, jurisdiction is more or less the GDP growth plus 1 to 2%. So, why do you think it should be the 1 to 2%? A simple reason is, as the economy, let's say the economy doubles, generally energy consumption will at least double. But then usually when economies are developing, there's also a shift from less energy intensive to more energy intensive methods. So agriculture becomes more mechanized. You start using diesel pumps and tractors and so on. Manufacturing moves from small scale to mass manufacturing, and so on, so on. And there's an associated trend of urbanization, people moving from rural areas to urban areas, or growth of urban areas, and therefore energy usage typically exceeds GDP growth by about a couple of percentage points, aggregated or averaged over the last 100 odd years, right? Okay, this is just publicly available data from IEA, and it shows the upper part shows essentially what are the projections of energy usage or energy demand. So if you sort of ignore the traditional biomass, which is the lowest, most brown row, or and then you can see coal is reasonably flat. There is some growth in green, which is typically the color used for oil in most of these charts, and then gas. And on top of that, some nuclear, some hydropower, and then some growth expected in wind, solar, and very little in modern biofuels. And I'll come to that. Renewable fuels and biofuels, there is some lack of clarity in the industry. Biofuels typically are made from vegetable oils and ethanol, or ethanol extracted from, and so they essentially have a food versus fuel kind of a challenge. And in many jurisdictions around the world, there is very active protest against using what could be food um, for generating fuel, and that those protests are sometimes or often led by NGOs or other entities, and there's a lot of commitment there from these groups to not use to basically saying there's a lot of undernourishment in the world, and it doesn't make sense that first world countries are converting what could be food into fuel for themselves, while there are millions around the world who are undernourished or starving. So biofuels, for several reasons. One is cost. um, uh, the inputs are costly. I mean, vegetable oils and all are actually, I mean, a liter of vegetable oil is a lot more costly than a liter of uh, petrol, gasoline, diesel, whatever. So the inputs are costlier than the product price, and therefore they have to be some kind of subsidies to help bridge that help bridge that gap. So biofuels probably will not see a tremendous amount of growth here for these reasons. So the large growth in sort of the non-oil and gas energy sources are eventually going to boil down to wind, solar, and some form of renewable fuels that are produced from wastes and residues, meaning things that can either not be used for human consumption or are truly waste and currently being thrown in landfills. So that's sort of where I think the sort of global consensus and the IEA predictions essentially are these. Yeah. So the very short answer here is oil and gas is not going anywhere. I mean, that's the way to look at it, right? Okay. Any question?
Yeah.
Any questions there?
There are a couple of questions already about what is the difference between the upper graph and the lower graph.
Okay. So I think there are different projections being made. One is a forecast which is based on, the lower one is based on stated policies today. So so let's go back to the upper chart. The upper chart essentially says what the world will need if there are no policy or regulation restrictions or limitations. Meaning, if governments don't control or restrict any of these things, or given, I mean, there is always an element of public policy in all of these, and I'll come to that. But essentially, the upper chart is where a realistic view of energy demand over the next, whatever, 25 years or so. The lower chart is given what is the stated policies of different companies, and therefore if these different countries, different jurisdictions, And if these stated policies are actually implemented, then what you will see is the lower scenario. In other words, everybody says we will cut down coal. And so if you see the lower chart, it shows a gradual reduction in coal consumption. Most likely, those stated policies will remain just stated, and the actual consumption will be as per the upper chart. Does that make, did I answer that question?
I was also thinking that this means that they're all predicting that they're going to increase the efficiency, so the demand is actually going to go down. Is that true?
Yes, from some sources, but not from all. So there's probably very little incremental efficiency gains that you could get from energy sources that have been used for hundreds of years or 50 years. I mean, there is really not much more calorific energy or calorific, that extraction that you could have from. I don't think coal will have any efficiency gains. It's probably already reached sort of the best possible efficiency.
No, I
there.
mean, if you look at your demand is 225,000 now per one, and the lower one has 200.
Yeah.
And
Yeah.
so that means that they want to increase efficiency, which reduces the demand.
Correct. Not in generation, but in usage. You're right.
For critical steam, that will
So
give you a little bit of higher efficiency on your fossil fuel steam cycles.
Fair. Okay. Any other questions here?
The upper graph says EIA, the lower one says IEA. Is that a typo, or are they different institutes?
No, hold on. No, the upper one is the. No, you may be right. No, I think
Or
both
they could be different.
come from.
Okay, same.
Yeah. Both are the same source. Yeah.
Okay.
Thanks for pointing that out. So both, you said there were 2-3 questions. There were other questions.
Subodh, you're muted.
She's asking what is the difference between primary and substituted energy?
Okay, that is a good question, and I will look for the answer. I don't have the answer right now.
Fair enough. We'll continue then.
Okay, thanks. Any other question?
No question, but Sundar has a comment
Sure.
who says that there is a trend to use cooking oil and wastes.
You
Yeah.
covered it. Rajiv, you covered it in the this.
Yeah, no, I'll address it a little bit earlier. Basically, here's the rationale, and the rationale is not necessary. So using inputs for generating energy or for generating primarily transportation and liquid fuels. So again, I'm jumping ahead. When we talk about energy, the focus in the public domain and most of the media is largely on transportation fuels, diesel and gasoline and electric vehicles, and those are the things that sort of dominate the media. Even though transportation fuels as a percentage of total energy consumption is significant, but it's not the only thing. I mean, a lot more energy is consumed in manufacturing plants and also for industrial and domestic heating and so on. But transportation fuels sort of dominate the media, and one of the things that is increasingly being done is to use waste and residues. So used cooking oil, distillers corn oil, etc. These are things that may not have no use, have very little use, especially for human consumption and even for converting to animal feed. So here's an example. Most used cooking oil, we don't realize, and this is also helpful for us to think about. If we continue reusing cooking oil in our house, fry something but save the oil, then fry something else, then save the oil, and so on. The used cooking oil absorbs a lot of metal, very fine metal particles from from the utensils. And these metals are essentially contaminants. And so for that purpose, used cooking oil essentially is a waste and cannot be used for either animal feed and obviously not for human consumption. So here's a very simple thought experiment. If you have a liter of used cooking oil, you can do 2 or 3 things with it. Number one, you can burn it. So used cooking oil, you just burn it. So you're going to generate CO2 and other waste products. I'm calling CO2 and other polluting products. Second, you can just throw it out somewhere and eventually it'll get oxidized and again it'll produce CO2. Third is you can throw it in a landfill and it will find its way either upward or downwards into water sources or to the surface. And again, it'll eventually get oxidized and produce CO2. Now, if you take that liter of cooking oil and convert it to a liter of diesel, you just eliminated the need for 1 liter of fossil fuel diesel. So your total CO2 generated in the world got reduced, right? So that's the driver for using waste and residues to generate fossil fuels, to replace fossil fuels, use renewable fuels, and especially if those renewable fuels are drop-in replacements, meaning your engines and don't have to be modified. You can either blend or use the renewable fuels as is, then that is essentially reusing, repurposing waste and residues. So that's an increasing trend. What again works against, I shouldn't say works against, but so that's the pro. The con side of it is again cost, which is collection of used cooking oil and other waste, then transportation, and then eliminating the metals or absorbing the metals out or cleaning the metals out, and then using it, converting it to usable fuels. So the cost part is holding it back. The plus side or the pro is that you are eliminating or reducing the amount of CO2 produced. Fair? Okay. Okay, switching gears just to give you a perspective of how big is, from a commodities perspective. So if you think of the total amount of commodities that are produced or traded in a year, since people are not stockpiling most of these things, then what is being produced is essentially being traded, is essentially being consumed. Other than perhaps gold, which is being stockpiled, you don't produce 100,000 tons of copper and then stock it somewhere. You eventually, in a year or so, or within a certain time, it will get sold and it will get consumed. So that's the relative size of these commodity markets. Again, this is emphasizing what I said earlier. The oil and gas, the role of fossil fuel oil and gas, or petroleum, oil and natural gas, may or will probably decline with time, but it's not going to go away anytime soon. So that's sort of what I'm getting at. Again, this is just another perspective of energy usage from typically fossil fuels, and I just put some standard conversion factors here for reference. And so you'll get, you can do a little bit of math if you wanted to and estimate, what exajoules, how many gallons of gasoline is that, or how many barrels or how many metric tons it is. I also put a couple of links here if you want to see. So there's the Independent Petroleum Association essential reference tools, and then for people who are a little more geeky and interested, the units that are used in the chemical industry, and those, just put some links over there. One interesting thing is that the US typically uses volume for all oil and gas measurements. So oil typically in gallons or barrels, and gas in cubic feet, whereas the rest of the world uses metric tons, and shipping uses only metric tons. So if you're going to send something by ship, by carrier, then the units used are metric tons. So again, there are lots of conversions about standard temperature and pressure, and how do you convert volume to weight and things like that. Okay. Just a snapshot of where we are in terms of supply and demand and what are the projections. It's sort of centered around, you could say, 100 million barrels per day total production, total supply and demand. The interesting thing you will see, I mean, you can draw all kinds of conclusions from here, but there's one very, one very obvious conclusion here, which is the generally supply tends to lag. Our estimate is between 2 to 3 quarters of demand peaks. So there's about a half year, a quarter to 2 quarters worth of a lag. And that's one of the things that swings oil prices up and down quite a bit. This imbalance in the short term sort of supply versus demand. So on this particular graphic, on the left side is the amount of absolute production in the world, and on the right side is the sort of the imbalance. So as you can see, these shaded blue swings, we are essentially talking marginal change of probably $2 million per day between supply and demand, but that $2 million extra production or supply and $2 million shortfall can swing the price quite a bit. So that's essentially sort of my perspective on commodity prices. And full disclaimer, I have never understood how or why oil prices move up or down so drastically. There is speculation, there is a cartel. All those things have an impact. All commodity prices have swings, but oil tends to be rather more volatile or interesting. Okay. All right, one more slide and then we can break for questions. So there was some discussion on one of the WhatsApp channels, about production and reserves and so on. And so I want to help anticipate a question or anticipate questions and help answer that. So reserves is proven commercial reserves of oil and gas, or what is called oil equivalent. In other words, you convert gas to an equivalent oil volume in a certain jurisdiction. And production is what you're producing on sort of a daily basis. So, and in most, if you draw a scatter diagram of reserves versus production, most countries would sort of fall on more or less around the diagonal around, but there are exceptions. So Russia does not have the biggest reserves of oil and yet is one of the biggest producers. And you will see in this list, Venezuela is missing. So Venezuela has low production or relatively low production compared to its reserves. So for various political, geopolitical reasons, and also how countries are organized and how national oil companies and what are called the institutes or organizations within countries that sort of govern or provide governance to the oil and gas industry within the country. What I mean is that there are some national oil companies, or most national oil companies. So Saudi Aramco is a good example, or ADNOC or KOC in Kuwait, ADNOC in UAE, and so on. Most national oil companies see themselves as the custodian of national wealth, of sovereign wealth. And therefore, their business drivers are a fine balance between conserving that national wealth or sovereign wealth, and at the same time generating enough production to generate cash for development of the country. Now, in some countries, you could argue that development is the development of the elite. The money goes to the pocket of the sheikhs. Libya was one such example. But you could also argue that money that's generated from the cash flow from production is used for development of the country. Malaysia is a very good example there. and international oil companies. So we are talking the big five being Shell, BP, Exxon, Shell, BP, etc., Chevron. And there have recently been a couple of very big acquisitions, so some of the companies have become bigger. But the IOCs, the international oil companies, are not custodians of any national wealth. And so their business drivers are essentially most efficient and maximizing production, because that's cash flow and that's money coming in. Now, the game that all these companies play is keep an eye on futures or oil prices and then produce accordingly. So the economics of production can be fascinating to observe. So there are times when a cut in production is therefore a cut in production produces an artificial scarcity or a scarcity, or upsets the demand and supply equilibrium, drives the price higher. So it's entirely possible that a producer, a country that is an oil producer, can make more money producing less, especially if it can impact or affect or control the demand and supply significantly. So the OPEC group, of countries have had or have significant clout. Some of that clout has reduced because the US has become one of the top producers in the world, and has therefore reduced, in some sense, the impact of OPEC countries. So it's fascinating in the sense that if one of the OPEC countries tries to, or I shouldn't say not one, the OPEC group together agrees on production cuts, then a couple of things have happened in the last few business cycles that we have sort of got some understanding of, but that's looking back in the rear view mirror saying this is what happened. So when OPEC makes a significant production cut, a couple of things happen. When possible, consumer companies or importers try to look for other sources of oil and gas, and there's a shift away from buying OPEC products and buying products from non-OPEC countries. And also, typically, there's greater incentive for oil and gas producers who are very nimble and agile as a whole. So the US is a very good example of very quickly responding to changes in sort of the perceived oil's future. And so the production ramps up or ramps down relatively quickly, I would say. And so those are the counterbalancing forces that prevent very wild swings in oil and gas prices. But then when geopolitics or war or restrictions imposed for political reasons, sanctions and so on, are superimposed on top of this, then the story becomes even more complicated. So a very convoluted way of saying movement in oil and commodity prices is complex. But these are sort of the big producers, other than the US, which is not shown here. These are sort of the big producers around the world. Okay, questions at this point?
Yeah, there was a question from BS, and I have several questions arising from that. So
Sure.
one, because US is missing over here, what is the reference production? I also wanted to ask in that connection about not only Venezuela, is it below 75 that you have removed it? Secondly, what about Iran? It is
Yeah,
not
so-
there. And also UK is a significant producer. It is not in this list. And I wanted to understand what approximately is India producing? Is it so far below, falls out of this list?
So short answer is Iran, Libya, and Venezuela are not included in this list. So this is not a list of absolute producers by volume. This is a list of essentially OPEC and non-OPEC countries that tend to collaborate. This is more from a price driver rather than pure volume production. Second part, you mentioned US production is hovering around 10,000. So in reference, it is one of the highest producers here. Third, I think India's production is low. Annual,
600,
sorry?
600 million barrels per day. I thought it's 600 or 500, 600.
Yeah, okay. Thanks. Yeah, so India is, the percentage being imported has gone up significantly. So we are one of the biggest, India is one of the biggest importers of oil and natural gas. Gas production has been declining in India at about 1% a year, which is a natural decline in the reservoirs, and no new major finds. And oil production is also declining. I think it declined about 5% in an 8-year period, 6% in the last decade. So, and of course, the demand in the country is going up. So the imbalance or the import percentage has gone up drastically. I think the last number that I saw was it was in the 80s. So 80% of India's oil is being imported. Okay, I didn't fully. Yeah.
There's a
Sorry.
question, I don't know if you're dealing with this later, about the strategic reserves, because where there's price fluctuation, and we know that the US and China have very significant strategic reserves. What kind of reserves are available around the world, and what is India's reserve?
So short answer, India's reserve is very small. I mean, to the best of my knowledge, it is so every country tries to maintain some strategic reserve. That strategic reserve, in many cases, is the final product. So you're trying to build up stocks of diesel and so on, essentially for purposes of emergencies, wars, etc. But other than that, significant strategic reserves are two ways of handling it. So one is that you have known reserves and you don't produce, right? But you have the ability to produce fairly quickly, so you can turn the taps on very very quickly. And then the way we think of the US strategic reserve, why it sort of comes up, is that almost all the, well, not almost all, almost exclusively all the oil and gas production in the US is in the hands of private companies. The strategic reserve is federally managed, so it's managed by the US government. So the US government is acquiring and then reserving, storing some amount of crude oil or products.
Rajiv, right now, though, India is the biggest incremental gain in oil production, oil consumption.
Oil consumption, yes. I mean, I have the figures in a separate presentation. I mean, so just a total aside, sometime back, 5 of us from different companies were asked to put together a review of this was through the Consulate General of India in Houston. They reached out to a motley group of 5 people. I don't know how they found the 5 people, to put together and look at sort of what is the status of what's the status of oil and gas industry in India, and how can the Indian Petroleum and Natural Gas Ministry of PONG, Ministry of Petroleum and Natural Gas, interact better with business in Houston. So I don't know what happened in the second part of the interaction, but the first part, which was a look at the oil and gas industry, so 5 of us did a little bit of work looking at the information that is in the public domain and released by the ministry and the Directorate of Hydrocarbons from Delhi. And then when we summarized that, we found that there was significant decrease in production on an annual basis. The sharpest declines were Bombay High from different reservoirs. But aggregated, there was a decline in production. And as Sundar said, probably the sharpest increase year over year of consumption in the world. And if I remember the hard numbers, we used to, in about 20 years ago, import about 68% oil. And I think, and I'm speaking from memory and I may be wrong, a few years ago or at 2020, it was, well, before COVID, it was probably 87% was being imported.
Yeah, it's 4 million barrels, above 4 million barrels of oil that is
Every day. Yeah.
consumed, and it's 1 million barrels according, I put a thing out there. But KG 97 may help a little bit. It should have gone online just a couple of months back.
Yeah. Yeah. And then there was a question about Iran. So Iran actually, I don't have the hard numbers, but to the best of my knowledge, is producing somewhere around 5.5 to 6. So 5,000 to 6,000, in that range. Okay, any other questions on sort of what influences prices, this particular cartel? And these are sort of consolidated, consolidated is not the right word. So sort of organized moves from these countries to impact or control prices through production cuts or production increases. Okay. Any other questions, anything? Okay. So a little bit of a perspective. This is sort of an aggregate of, if you take all the crude oils in the world and average them, this is probably what comes out of them. Now, the lighter crude oils, which have shorter paraffinic chains, will produce more of the lighter components, and the very heavy oils will produce more of the heavier components. But this is a fairly good sort of percentage, percentage distribution. So I would not look at the decimal point with a lot of accuracy, but it's reasonable to say 35% of a barrel gets converted to petrol, 25% gives diesel. The marine fuels are heavier than diesel, and then kerosene is processed or cracked to make jet fuel or aviation fuel. And then some of the lighter paraffins, typically ethane, butane, propane, butane, get converted into ethylene and propylene and so on. And then those become feedstocks for a lot of plastics and synthetics and so on and so on. But this is just a rough idea of by volume, what comes out of a typical barrel of oil. Fair? Okay. Questions here? Or let me go a couple of slides. So, like I kind of said, crude oil through typical petroleum refinery, these are sort of the products that come out from the refinery, and then these feed petrochemicals and so on going forward. So the words, the terms used here are the terms that are used in the industry, and let's not get caught up too much on sort of what is fuel oil and heating oil. But just to give you an idea, LPG is in the propane, butane kind of range. So if you look at paraffinic chains from C1 to about C60, C70, then the top is going to be C2, C3. Gasoline is around the C8 to C kind of 12, 14 range. Diesel is typically C16 to C22 kind of mixes. And then as you go heavier and heavier, you end up in what's colloquially called fuel oil or heating oils and so on. So marine, the very large ships, they either sometimes they burn diesel, sometimes they burn a combination of diesel and sort of the fuel oil there. And then very much at the bottom is sort of asphalt, which is at room temperature and condition is a solid. And then one of the byproducts is pure coke in sort of in some refineries. So a complex refinery will probably produce a lot of these things. Sort of a very simple diagram of a refinery is the very first step in almost all refineries is a distillation column. And so a distillation column is pure mechanical separation. There's no chemical transformation there. And if you see, there's a word called SR used here, or not a word, I mean, an acronym of SR used. So you take crude oil, you try to remove, separate the water out of it. The salts are typically dissolved in the water component that comes along with crude oil. So there is some mechanical cleaning, desalting that happens there. And then goes to a distillation column. And SR here stands for straight run distribution, meaning no chemical processing. It's just a straight distillation. So on the top, the gases are typically 90, 100 degree Fahrenheit. And at the bottom, the gas oil is probably 700, 750 Fahrenheit. So so by temperature, these things get sorted out. And then the almost all refineries have catalytic cracking or hydrocracking. The difference between catalytic cracking and hydrocracking, both have catalysts that help in cracking the longer chains and making shorter chains. Longer chains are less valuable. And the shorter chains are more valuable. They have, from a fuel perspective or from further processing. So both catalytic cracking and hydrocracking use catalysts in the process. The difference is that in hydrocracking you introduce hydrogen, and so the hydrogen does one out of two things. It either eliminates or it combines with and removes any oxygen that's in the chemical compounds, or it helps in creating breaking and making stable smaller compounds out of longer compounds. And then there are a couple of other processes that take place. Reforming essentially is isomerization. So a straight chain becomes an isomer or a branch chain. And that essentially helps in driving up the octane value, driving up the cetane value, and so on of gasoline and petrol that's produced. The term gasoline is a generic term that is what we call the lighter fuels. They are typically blended, and essentially that's what's available. In the Middle East, it's called gasoline. In the US, it's called gas, and most of the world, you call it petrol. There are the next sort of group is called distillates, light to heavy distillates, and those are kerosenes, which are further separated or processed to make jet fuels, aviation fuels, and then diesel sort of. So that's the distillate range. And then the heavier oils are either cracked or sometimes they are sold without much processing especially if they are going to be burned. Burning in furnaces and cement plants and steel plants and so on. When you want to use it in engines like marine engines, you need to have the specs are tighter than for fuel oil. I mean, that's sort of understandable. And at the bottom, typically you will get asphalt as a product, and then waxes and greases of different sorts. Okay, any questions here?
So I presume that the heavier oils have a high energy density, and that is why they're being used, for instance, in jet fuel.
So the lightest is okay. That jet fuel is
Ester oil
actually jet.
is not used in
Yeah,
in aviation oil. So basically, aviation oil is very light, and you do a kind of alkylation, which there's a HF process and other processes to get that. It's normally from the lighter ends. The heavier
yeah,
ends are the high coalish, like
yeah,
more carbon, less hydrogen.
yeah.
Can
So
I come in?
yeah,
Saurabh,
go ahead, please.
I worked in a refinery for 35 years, so I know these things. I'm saying that aviation fuel is nothing but kerosene treated for some impurities that has to be removed. And the flash point and the freezing point, which is the temperatures being very low at the higher level and where the planes are actually moving. So it is only to meet that. Actually, aviation fuel is nothing but kerosene.
Yeah.
And the lighter fuels have got definitely more energy intensity in terms of calorific value. They border around 11,000 to 12,000 kilocalories per kg, whereas the heavier ones, like the furnace oil that is at the bottom end with heavy chain molecules, they are around 10,000 kilocalories per kg.
But then why not use petrol for aviation fuel? It is even lighter.
The flash
Well, you
points are
have to have
higher.
very high specs. For example, to put even an additive into a jet fuel, you cannot do it unless you basically you test it. Okay, so we put drag reducer for the line that supplies LaGuardia Airport. And there is a basically LaGuardia Airport's takeoffs and landings are limited because of the amount of jet fuel they have. When we had to put that in, we had to go and test that on an engine. Was count of $200,000 or $300,000 to do that test to qualify our additive. Jet fuels are the specifications for a jet fuel are tremendous.
There are some 45 or 50 tests that need to be completed before the product can go out. And before it is loaded onto the plane, there are some 7 or 8 tests it has to pass before it is loaded on a plane every time.
So typically, if you produce a pure paraffinic kerosene or synthetic paraffinic kerosene, SPK it's called, which is not produced from fossil fuel, but let's say it's a renewable process. In order to have it accepted as a jet fuel, today there are several restrictions. So the Federal Aviation Authority, FAA, which is de facto sort of the governance for air transport, commercial air transport around the world, it mandates that you must have a minimum of 50% blend from fossil fuels, and you have to have a certain aromatic content. So you must have sort of the benzene, xylene, toluene kind of um, aromatics in it. And as Sundar said, the two most critical components are the flash point, which is the temperature at which it can catch fire or it will, and the cloud point, which is essentially the lower temperature at which it starts solid, there is solidification taking place, so it becomes cloudy. And so the cloud point restricts transportation. So if you want to, I mean, even in petrol, you adjust the blend for summer and winter for some of these properties. So if you look at, if you are trying to send petrol or diesel to, Canada or Montana in winter, your cloud point needs to be really low. Otherwise, the diesel will just turn to solid and clog all your pipes, and so on. So those kind of specs are very tightly maintained for aviation fuel. So thank you for that.
I mean, just as a thing, in the US market, my company provides 60% of the fuels that you're using in the US market are provided, have additives that are produced by my company.
Yeah. So Baker Hughes, and I think RTI is another company that, but Baker Hughes is sort of the dominant player in terms of providing these additives. One other term that you will see here is naphtha, and naphtha is sort of the industry term for a certain light product that is produced as a almost as a byproduct of some of the cracking and distillation processes, and that's typically blended into. It's too light to be blended into diesel. In fact, heavy naphtha is an off-spec naphtha, and that's typically blended into gasoline to improve some of gasoline's properties. So apart from flash and flashpoint and cloud point, which Sundar mentioned, a key sort of performance indicator for the gasolines is the octane number, and for the kerosenes or diesels in particular, it is the cetane number. So it's you manipulate is not the right word. You adjust those properties by blending and by putting in the right components to get the desired octane value and the desired cetane value. Okay. Any other comments? Any other suggestions? Sundar, Sundarajan, Sundar and the other Sundar. Any other inputs?
Nothing. You can go ahead. No problem.
Okay, thanks. All right. So this is sort of a broader picture of, we always think in terms of, we think about transportation quite a bit, but then oil and gas is, it's not just transportation fuels. So a very significant portion, almost half of what the oil is produced is not transportation fuels. And, pharmaceuticals and plastics and synthetics and rubber, natural rubber is latex is used in very few products. Almost all the rubber, the primary, they are all blended or synthesized. And here's just sort of a list of everything that is kind of made with oil, or out of downstream petrochemicals or other processing. So here's a cartoon that essentially shows, again, this comes from the oil industry. So, take it, it's biased, but it essentially says that in modern living, almost everything we carry, use, has some element of, has some source of something that has originated or has been sourced from fossil fuels, right? This is an actual photograph of a person who protests against oil and gas. He had an accident and he's in the hospital, and somebody very smartly said, here's this person protesting against oil and gas, and almost everything surrounding him has something to do with petroleum. Anyway. All right. Any questions about this? Any comments, suggestions?
I mean, one comment is that many of these products do not contribute to global warming, except for the energy demand and the
At the
heat.
production and transport part.
Yeah, but the plastics itself, they're not creating CO2.
Yeah. Okay. Thanks. Good comment. Okay. So coming back to sort of the energy transition. So the energy transition essentially is away from fossil fuels and towards cleaner energy sources. So, I mean, I just put down what is my perspective. It's very, it's deliberately imprecise, which is, yes, I think the transition is happening and will happen. And I think the challenge for all jurisdictions, societies, countries is how to navigate that transition, at what speed, scale, and And then any public policy that's framed always has some winners, some losers. The word winners is missing here in this paragraph. For some reason, I lost that. There are always winners and losers. So you frame any policy pro or con, and somebody somewhere has an economic advantage and somebody else has a disadvantage. Or if it's not economics, it's pollution or it's health or whatever. So the interesting thing here is that a lot of discussion that I see on going on in the media and more so perhaps on social media, it seems to be people latch on to one dimension and that's all they're thinking about, right? So there's a lot of talk about, hey, lithium batteries involved so much in mining, and there are kids in Africa that are going down and mining for these rare metals and et cetera, et cetera, et cetera. And I think the reality of any energy policy is that you have to take into account many different interests, and they are often conflicting, and therefore framing policy is not easy. And it's, you can disagree with the policy, but generally some thinking has gone into it. So different jurisdictions, adopt different policies, and you can see that between countries, and you can even see it within a country. I mean, California is different than Texas. I mean, they value different things, or they have different, what I call, business drivers or policy drivers. But here are some of the things to think about. So obviously economic growth. So at the big picture, the developed countries have already, they have achieved a certain level of well-being for their populations, and for the last 200 years have very happily polluted the earth. And if they turn around now and tell a developing country not to do so, well, that's that's a value, that's a normative discussion. They are saying, is this justified? Should why not me? And why should I not develop my population and look after my people, even if it pollutes the earth and so on? Second, obviously, is the localized impact on water and air and water pollution and essentially health. And that's from all sources, all possible sources of energies. And then there's the consideration of the lifetime cost of ownership, for different things. So nuclear plants, the decommissioning is, the operating cost is low, but the commissioning and decommissioning cost is high. Similarly, you can argue in loops that how much energy is used in building a windmill, and what does the windmill deliver? And so there are all these kinds of pro and con considerations. So and yes, the other factor which Sundar just mentioned is the greenhouse gas emission and heating examples. And again, this is something that we can and should talk about because it brings clarity to our thinking. But here's some examples. I took a couple of examples to illustrate that something that can be bad in one way can be very good in another way, and that's the challenge of policy formulation. So electric vehicles use batteries, and we can all argue about the lifetime cost of battery ownership and the disposal of batteries that go bad, disposal or reuse and renewal or whatever you call it. So there is an argument to be made that EVs use batteries and that there is a cost associated to having those batteries. But on the plus side, EVs cause zero pollution when they are, or negligible pollution when they are being operated. Whereas a diesel truck that runs through your neighborhood is going to be spewing contaminants in your environment. So if diesel trucks are running around your neighborhood or your schools, then your children are getting a certain amount of pollution from them. Whereas the pollution associated with building or constructing things that go into EVs can be highly localized and therefore hopefully better managed. So those are sort of just theoretical or thought examples or thought experiments to say that not everything is black and white. There's a lot of complexity here. So the other example here is Windmills, when they reach end of life, which is probably around 20 years for most windmills, well-designed modern windmills. There's a lot of disposal costs. All those big blades have to be chopped up, and the fiberglass, blah blah blah. It's not biodegradable. You can make a lot of noise about how bad the windmills are when you look at them from what goes into their construction and what happens at the end. But the reality is that when the windmill is operating, it is generating zero CO2. It doesn't cause any pollution. It doesn't spew any contaminants. And to produce an equal amount of energy, 1 kilowatt hour from a windmill versus 1 kilowatt hour from coal generates about 1,000 times the CO2 that a windmill will produce in its lifetime. So those are the pros and cons. So my whole intention of trying to put the energy transition here is to say there are no straightforward answers. Don't latch on to one dimension. It's a multidimensional problem, and that different entities and jurisdictions will arrive at different solutions, and at different times those solutions will change. And yes, politics comes in, and sometimes countries make wrong choices, and one can argue that Germany did a wrong thing by going away from nuclear, and then you talk to Greenpeace or some other NGO, and they will say they did the right thing by going away from nuclear. So, in short, it's complicated. That's the point I'm trying to make over here, that almost any of these decisions, pro or against, it is a multidimensional decision, right? So we talk about, you can make PowerPoints from coal and then put all kinds of electrostatic, capturing devices in the smokestacks to capture all the pollutants that go out. Well, not all gets captured, and there is a reason why coal plants are not put in the middle of Connaught Place. If coal-fired electric plants have to be put up, there's a reason why they're not put in the middle of residential areas. I mean, so my contention here is that there's a lot of complexity. It's continually evolving. What's right today will not be right 5 years from now. And of course, technology will make an impact. I mean, if we can reduce the amount of energy that goes into producing windmill blades, or find a better use for the used blades, or etc. I mean, the equations will change. So cost and technology, or technology impacts and costs, are obviously great determinants, but then there are other considerations, and different jurisdictions adopt different considerations. So one particular state or country may value reduction in greenhouse gas above many other things, and be willing to pay more for something that reduces greenhouse gases. Another country may not. So, and that will always lead to discussion and arguments, and sometimes heated arguments, but that's the reality. Okay, questions here? Comments?
Yeah, I had a bunch in the chat. I don't know if you can look at them and decide which ones to answer.
Let me see if I can see the chat. Okay, so there's one question saying, okay, there are lots of questions, but let me start from the bottom up. So reduction in oil demand should be acceptable to oil producers since it extends the life of their oil wells. Again, yes and no. So here's sort of the perspective. If you are an independent oil company, or you are one of the mid-sized to major international oil companies, reduction in demand essentially means reduction in cash flow. And again, it's a balance between, like in any business, how much do I want to keep in reserve, what's on my balance sheet, versus how much I'm generating, and if so if I have the choice okay, forget oil. Let's just say that, I'm making bread and I have a certain amount of reserve. I mean, if the price of bread goes on, I want to cash in on that. If the price of bread goes down, I probably want to slow down my production and adjust to the market accordingly. And I think those considerations will apply more to oil producers that are driven by cash flow versus oil producers that see themselves as, like I said, custodians of the country's wealth. So an oil producer like Aramco, it's essentially indistinguishable from sovereign wealth. I mean, Saudi Aramco's wealth is Saudi Arabia's wealth. I mean, that's, those are very blurred boundaries. So not necessary. Again, it's what can I get today for producing versus what can I get tomorrow from producing the same thing. Also, not producing doesn't mean there's zero cost. There is associated cost with maintaining and just pure maintaining oil fields, even if they're not producing. So everything tends to let's go back. In terms of geologic, this is a big question. Okay, so the question here is, over the last few decades, known reserves have consistently gone up, so there is no longer talk of peak oil. In terms of geological and exploration knowledge, what part of possible reservoirs are still unexplored? In other words, are future increases in reserves likely to come from new discoveries or new methods of extraction like fracking? So on a very long, if you look at 100+ years of oil exploration, let's not talk of 1800s, but let's just take from 1930, which was roughly where oil was discovered in Saudi Arabia. From the 19th, let's take the last 100 years. Essentially, in the last 100 years, what the industry thinks is the easy oil has been found. In other words, reservoirs that were either very good quality reservoirs, meaning they have high porosity, high permeability, so that the porosity essentially is storage space or storativity, and permeability is the ability to flow or interconnectedness. So what you want is large capacity, full of oil that flows very easily. Those are the best reservoirs. And if it's naturally pressured, then it'll push the oil out once you make a hole into the reservoir. So those are sort of the best reservoirs. And on the second dimension is how easy it is to get to the reservoir, meaning they are either on land or they are in shallow waters, so it has been relatively easy to reach those reservoirs. The general assumption in the industry is all that easy oil has been found decades ago, which means today you either have to go to poorer rock quality, meaning poorer quality reservoirs or marginal reservoirs, or you have to go to more difficult places, physically more challenging to get to the reservoir, which is either deeper water or it is, like very high latitudes, north of Canada, Alaska, etc., or very remote regions and so on. So both these essentially place a challenge in terms of additional reservoirs or additional reserves being discovered. So the short answer is yes, we will almost certainly find more resources, which will be commercial, and therefore our commercial reserves or proven reserves will increase globally. It's also probably true that those reserves are almost certainly going to be more marginal or difficult reservoirs, meaning the rock quality or the porosity, permeability, and a few other things that determine rock quality are not that good, or those reservoirs are likely to be in places that are more difficult to reach, first to explore, then to produce, then to transport the produced oil. Associated with reservoir quality, there's a combination which is the rock part of the quality and the crude part of the quality. So you can have a good rock fabric. The mechanical properties of the reservoir are very good, but the crude inside is bad or not as good. So one is it could be too viscous, very heavy. Second is it could have a lot of contaminants in it, and the most damaging there is either very high amounts of CO2 in the reservoir, which is very corrosive, or very high amounts of H2S in the reservoir, which is also very corrosive and poisonous.
But I mean, on the CO2 and H2S, I mean, 1/3 of Exxon Mobil's production is sour gas.
Yes, that is true, and so that is true. It's just that it adds to the cost and the complexity of the production. So, for example, you have to use chromium steel. You can't use high carbon steel. You have to use scavengers or absorbers or things that prevent or minimize corrosion. So, I mean, Sundar is the expert of the experts on corrosion. But let me skip back and share with everybody. I think I had a slide here, which was, yeah, it's the next slide actually. Let me go back. So literally the next slide was, this is, so you can see, oil qualities or crude qualities plotted on this in terms of how light is the oil, which means easier to produce and produces more of the high value lighter components, versus how much how much associated contaminants or sulfur it has. So this is a pretty decent example of some of the heaviest oils and some of the most the highest H2S content or highest CO2 content oils are from prolific reservoirs. I mean, a lot of the Saudi Arabia, this Arab formation, as it is said, I mean, it's a prolific reservoir. It's one of the, not just huge, but it's a mega reservoir. And yet, if you look at the quality of the oil that's produced, it's relatively heavy and has a lot of H2S in it. So what is called the sweetest, lightest oils, I mean, they're really good quality, sort of very good quality oils from that perspective, that the cost of producing them, which is from the steel and everything else that's used, transportation and processing is, I mean, cheaper. So the break-even point per barrel of oil, is different for different crudes, and I think that's the break-even point depends on the crude, of course, and then where it's located, meaning how difficult it is to get a drilling rig there, and how difficult it is to transport the produced crudes or oil or to a processing facility.
So in Guyana, there was a find in 2015, which is said to be very significant. Is it in very difficult terrain? Why was it missed all these years?
It's offshore.
It's deep water.
It's offshore.
It's deep water offshore. And so in Latin America, the bulk of the offshore work so far had been in Brazil, or off Brazil, actually, technically, offshore Brazil. And Guyana is deep water, and as a country, it did not have, it's a third world country, it did not have a lot of sort of resources to manage. And it's only 6-7 years ago 8 years ago, I think, 7 years ago, 2017. So probably 6 to 7 years ago is when the first tender for development work. That means exploration wells had found oil and it was considered commercial. Now you want to develop the reservoir. I think that development of that field,
Success.
yeah, 2016 probably.
And in fact, right now it's at 500,000 to maybe going to be 1 million barrels per day. We lost just recently some tender there.
Yeah, and so it is deep water. It's the infrastructure in the country is negligible. So if you want to send, so 6 years ago, you wanted to send 1,000 people to work there. Well, there were no hotels. There's no place for them to stay. The infrastructure was negligible. So when that happens, the oil companies basically have to go in and build some minimum infrastructure, build airstrips, build roads, build hospitals. So a combination of those factors.
So, in this case, want to have more oil drilling in Alaska and things like that. So, the government policies can actually issue permits to explore and things like that, and or you can stop it. And so, basically, policies can change how expensive it is to drill for oil too, right?
That is correct. That is absolutely correct. There are sectors that are unexplored even today, and for whatever reasons, there are governments that are very slowly opening up certain parts of the country, of that particular country, for exploration work, and they are restricting who can explore, who has the rights to explore, who will have the rights to produce. So if you look at Saudi Arabia, the whole landmass, you can see that there is a prolific field, the War field, on sort of in the middle of on the eastern side, and then on the fringe of that entire landmass, you have Bahrain, you have Oman, UAE, Oman, and then what used to be North and South Yemen. And there's an entire a fourth of the country is unexplored. It's called Rub al Khali, which literally means Khali or empty quarter. And there's been very little and very controlled access provided there for some companies to go in and start doing some preliminary work. Nobody knows if there's oil and gas there and how much. It could be zero. It could be the next biggest thing. Nobody knows.
No, there was some production. There's
There's some.
There is production from that area.
No, but it's a very small part. It's like even the seismic density there is very, very low. So it's relatively unexplored. I mean, if you think in terms of how much seismic coverage there is and at what sort of density, that's very low. And there are parts like that around the world that are still sort of relatively unexplored. There's also one very big source of energy which we won't call petroleum, but so far I think there hasn't been. It hasn't reached. It's kind of academic. It hasn't reached commercial scale, and that's called hydrates. So hydrates are essentially methane that is trapped in ice crystals in the subsurface. So there's a certain temperature and pressure window. When you go from the surface of the earth and you start going down. On land, you will see the temperature will keep increasing linearly as you keep going down, towards the center of the earth, obviously. But on sea, there is a slightly different phenomenon because
This is actually a problem for global warming. There's always a worry that if you really do warm,
all that methane
Permian extinction was caused by degassing of natural gas hydrates. There are huge natural, like outside Japan, there was a research project to mine those
Yeah.
hydrates, even North Carolina around their area, that area. But that's more of a, I think, a problem than a real thing, because if we hit a certain number, that could be a bad thing.
Right. So I think what Sundar is saying is, so hydrates are essentially, you could say, not is gas that has been trapped in sort of water that is turned mushy or turned to ice. There's a certain temperature.
CH4 plus H2O gives
Yeah.
you the CH4 H2O crystals. That's
Crystals, right? So it's essentially, and here's sort of, I think, the big unknown. So if you can, at a reasonable price, you have the technology to tap into it. You have a source of methane, a controlled source of methane, which, I mean, the amount of hydrates present in the world's oceans or seas is phenomenal. But if you don't control it, or you can't control it or extract it, and the other event happens, which is you reach a tipping point in temperature, then all that methane gets released. And methane is, its global, its warming effect is about between, over a lifetime, it's over 70 to 80 times that of carbon dioxide. So, the amount of greenhouse gas effect that methane will have is, I mean, it's mind-boggling.
You're saying that there are these crystals in sea water, or are they at a certain
At
depth?
the
Are they
bottom of the sea. At the bottom of the sea. In fact, if you see the Gulf of Mexico seeps, I mean, in fact, National Geographic has an article. You'll see these seeps of methane which come around that. Actually, around some of those areas were actually some of the first Gulf of Mexico finds. Yeah, so methane plus water will give you these different crystals. There's a type 1, there's a type 2 hydrate. There are different crystallographic forms of the hydrate. And if you have sufficient pressure, you get these hydrates, which,
Right.
is a problem in natural gas actually processing. You have what we manufacture, what are called low dosage hydrate agglomerates and things like that, or kinetic hydrate inhibitors. But those are all formed at the bottom of the sea. There's methane crystal, the methane hydrates, as well as their carbon dioxide hydrates.
So, Srinivas, just to add that, so just below so if you look at the sea bottom, that is, at a fairly low temperature. And then as you go deeper, so the temperature profile from the surface of the sea, from mean sea level, on land is going to be different than in the sea because of the water, right? So just below that water, there is a temperature pressure window where these hydrates are formed and sustained. If the pressure is too high, they can't form, and if the temperature is too high, the CH4 and the H2O dissociate, and the methane will escape. Will. So it's like almost I mean, I've seen a video. I've never seen it in a lab, but it's almost like a gelatinous sort of crystals that are formed, and they are in the subsurface below the seas, and they are huge in sort of area. I mean, we are talking millions of square kilometers of such hydrates exist. And so along the Konkan coast of India, offshore Karnataka, they are estimated to be huge hydrate deposits, and so on, so on. So, I mean, I'm just throwing out that there are other non-petroleum sources of energy, and it's not that they are not known. We know about them, but there hasn't been a commercially viable technical solution or technology to extract that and put it to use. And yet the risk remains. Yet the risk remains that if there's warming of the oceans or something happens, beyond a certain point, that all of a sudden you'll have a methane blanket, and that'll be the end of the world, as we know it.
I had a question about fracking, because I believe a very significant portion of the US production is through fracking. I heard that when the oil prices crashed some years ago, that many of these facilities had to shut down because their cost of production was too high in comparison to the market price.
Yeah.
One, what is the state of those units now? And secondly, why do we not hear of fracking anywhere else other than the US? Is it because there is special geology in US? What is the reason?
Okay, so first I'll take a minute and explain what is fracking. And so I talked about reservoir. I'm going to make it. I'm trying to take the jargon away and explain in a very simple fashion. We talk of a reservoir as being literally a place where oil and gas can accumulate and be stored, right? It's a reservoir, right? It's a reserve there, a small. And it has to have two components at least. It has to have porosity, meaning it has to have pore spaces or voids uh, inside that rock fabric, inside that rock matrix. And it has to have connectivity or permeability, meaning it has to have some ability for one pore to connect to another pore, to connect to a third pore, to connect to a well bore where you have drilled a well. If there is no permeability, you will drill, and whatever is very close to that oil well will flow into the oil well, but everything else has no connectivity and will not come. Now you have certain types of rocks, colloquially they are called shales, that have some porosity but have very little permeability. So you have pore spaces that are more or less isolated. They're very poorly connected. So there is something there. It could be water, it could be gas, it could be oil, but it will not flow because there is no connectivity. So fracking essentially creates a fracture. It creates a mechanical crack in that rock or cracks in that rock that allow flow to take place. So what is locked and was not able to flow naturally, or even with applying pressure from behind was not able to flow, now by creating fractures, you have interconnected or connected all those, not all, but a substantial portion of the pores. So the first kind of reservoir is called a conventional reservoir, which has porosity, permeability, has some reservoir pressure, and you can sustain that pressure by injecting water, carbon dioxide, or take the produced gas and put it back in to push the oil up, right? To create a reservoir. So essentially, it's a reservoir that has a combination of the right rock type, the right thickness, porosity, permeability, some self-flow potential, or et cetera, right temperature, pressure for the oils not to be very viscous. The other kind is unconventional, which is typically either very low porosity, and typically with low porosity is low permeability, or it has porosity but no permeability. And shales are usually a large class of rocks that are colloquially called shales. Chemically, they are a mix of, or not chemically, mechanically, they are a mix of very fine particles, which are clays, and slightly bigger particles, which are silts. And then even bigger particles are sand grains, right? So they are typically have very fine clay particles. And what the clay particles end up doing, and this is a very simplistic explanation, so don't beat me for talking about it this way. The clay particles essentially block flow. They're very small particles, and they choke all the flow paths if there were flow paths. And the way shales are deposited and compressed to become rocks, the clay particles find their place and kind of block the flow. So sort of the short answer is shale formations or shales may have hydrocarbons, typically will have hydrocarbons in them, because there is not enough permeability. Those hydrocarbons would not have migrated out, meaning they are in situ, they are there. And to reach them, you have to frack. And there are very large shale formations in the US. There are very large shale formations in Australia, in parts of India, especially on the eastern side of the Deccan Traps. There are very large shale formations in Russia, China, and in Europe. very large shale formations in Argentina in one part. And Sundar, please correct me, there must be shale formations elsewhere. Now, Europe, there are restrictions on fracking. EU does not permit fracking. And except on a very small pilot scale, there has been something. So shale formations in the European landmass typically are you are not going to get there. Australia has tried fracking. There is some amount of fracking going on in India, but the amount of oil and gas being produced is very small. It's negligible. It's like a pilot project. You can more or less say few drilling rigs. 5 drilling rigs are looking for coal bed methane and for shale gas.
So, the way I understand is that fracking is actually can be a secondary uh, recovery process. So even the conventional reservoirs, after they're depleted some, you could still use fracking to get the some more
Yes.
after.
Yeah. So the fracking, the way Saurabh had asked the question, was primarily shale, but fracking and acidizing are also for conventional reservoirs, especially for the carbonates, for the limestone dolomitic kind of reservoirs. So typically, here's going back to very basic sort of building blocks, and I'm very mindful of time, and I'll try to wrap up in the next few minutes. So if you think of sand particles, they are essentially silica with some stuff. And don't want to go into it. There may be pyrites, there may be something else. And if you think in terms of two pieces of silica or two pieces of quartz, they will not stick to each other. There's no chemical. SiO2 is a very, very stable compound, and there's no sticking. So you need something in between to bind the two together, and that's called a typical cementing material. So that may be a carbonate, that may be organic material like gunk, literally, or it may be clay particles. So the sandstones, the sand grains are made up of sandstones are made up of sand grains are made up of basically silica particles and few other things. But the sand grain to sand grain interface tends to be mechanically a hard interface with not much give. There is no compression possible there. So sandstones typically end up, let me put it this way. Because of the structure of the grains, you typically end up having higher porosity, meaning when you put tons and tons of pressure, those grains just don't move. Like, if they're shaped like this, they don't move. So the space between my hands is a pore space, and between my fists. And tons and tons of pressure does not collapse them any further. So you end up typically having higher porosity in those kinds of sandstones, especially if the grains are angular and sort of misshaped, to use that language. Carbonates, on the other hand, have two origins. They are either organic, which is like, like reefs and so on, or inorganic, which is you have a solution, you have a certain carbonate in solution in water, and it's let's say standing water, and the temperature changes and the carbonate drops out of solution. And or you have some kind of evaporation. Evaporites are typically salt and gypsum and so on, but carbonates have both chemical deposition as well as organic origins. And carbonates are they have, okay, I don't want to go into that level of detail, but let's just say that carbonates can be compressed more because the individuals carbonate grains, either they are grains, they're even carbonates that don't have grain structure or a very well established grain structure. So on average, the porosity in carbonates and the permeability in most carbonates around the world is lower. Exceptions are Bombay High, exceptions are the limestones in Saudi Arabia and so on. But so there's a range. You have very high porosity, very high permeability, beautiful carbonate reservoirs, and you have marginal carbonate reservoirs with low porosity and lower permeability. So those then become candidates for either acidizing, meaning you inject acid, which eats away the carbonates, or fracking, or a combination of fracking and acidizing. So what Srinivas said is absolutely right, especially when the initial production goes down, you stimulate the reservoir, stimulation by fracking, acidizing, doing acid washes, things like that. So that's more so in carbonates. Acidizing in sandstones generally, I mean, it's done rarely because you only will use it to flush out or remove some of the organics or some of the calcite. The silica itself is not affected by acid, so you can't do much to the matrix of the rock. Okay, any more questions? Okay, so one unanswered question from Saurabh was about shale and why it's in the US and not elsewhere. And I think that it's US producers have truly, smaller producers have truly been entrepreneurial and have, through trial and error, figured out the economics of producing best from shale formations. Some of that learning is available to others, and some other countries will have to learn on their own. So, shale production, coal bed methane production, these are in outside of the US. Shale production, to the best of my knowledge, is a small percentage. It's not that shale formations aren't there. It's Russia, for example, has so much other good quality rock that they don't want to go to the shales. Why should we go to shales when we can produce so much more from conventional reservoirs? Saudi Arabia has got a lot of shale formations. Okay, any more questions on this?
Rajiv,
Sure.
Rajiv, can we finish this presentation? Then we'll take the questions later.
Yeah, no, I mean, I'm done. This was literally my last slide, and the appendix is sort of meant to be a separate discussion altogether.
Okay.
I'm done on, I mean, I'm just, if there are questions, I can take any questions for the next few minutes, and otherwise, thank you for your patience in listening and asking questions. I jotted down a couple of questions that I did not find answers to, and if I can find them, I will post the answers there. One was about
question.
DS, you have some questions?
I have a question.
Sure.
See, most oil prices are fixed with reference to Brent crude. Now, why is that? Is that historical or is there some technical reason?
No, Brent and WTI, which is West Texas Intermediate. If you see the quality of the oils, I had it here. So the United States WTI and North Sea Brent are right at the bottom. So they are relatively light and are sweeter crudes. And that is just a benchmark established over the years. North Sea used to be a fairly significant producer about 2 decades, 3 decades ago. Now it's all declining, and the majors have sold off the fields to smaller players who have then extracted more oil and then sold it off to even smaller players and so on. So it's essentially, other than the Norway sector, the UK sector is kind of, it's declining. But those were just the reference points or benchmarks. So you just say, the WTI price is more or less, and everything else is typically reference to that and will be very different. So, the oil coming from Iran will be several dollars per barrel different from WTI prices, but and the WTI prices that are quoted at a particular physical point. It's a collection and distribution center in Cushing in Oklahoma. And it is, if you buy a barrel of oil, well, you can't buy a barrel of oil, but if you were to buy 1 million barrels of oil or whatever at that point, then this is what it would cost. And if you want to buy it 200 miles away, then the cost the price would be different because of the transportation cost and so on and so on. So no, those are just two reference points because historically Brent was sort of a significant producer that was being traded in the Western world. I mean, that's my way of thinking.
So, Caps, quick question on the economics of it. I mean, if we look at there being 42 gallons per barrel and an approximate price of, let's say, $84 per barrel, that's about $2 per gallon right there for the raw petroleum, raw crude itself. How, I mean, does that sort of, I mean, I'm assuming gasoline would be the more expensive output of such a barrel. And if that's the case, then does that set a bottom price in terms of something like, I don't know, $2.5, $3? Can it go lower? And how much profit lurks in there, even at a price of something like $80?
So two parts to the industry, the upstream and the downstream. Again, it's a simplistic sort of answer, and then I'll come to your specific. So when the market price of crude oil goes up, the upstream producers' margins improve and the downstream refiners' margins degrade. So what is output for one is input for the other. So when the crude prices go up, upstream companies make money, downstream companies make less money, right? The downstream part of the business makes less money. Secondly, the cost of there is still money to be made by downstream. So upstream companies will make money when the price of oil is $80, right, or $70 as is today. Bear in mind that to use IIT language, the worser crudes have much lower price than what you see quoted, which is WTI or Brent. So some of the heavier crude, some of the sour crudes have significantly lower price per barrel than the 80. And downstream companies still make money out of it. Otherwise, they wouldn't be in production. So the cost of the most public. So there is a consortium of refiners in the US, and they do publish sort of fudged, I shouldn't say fudged, but disguised figures. So the processing cost per barrel for good quality oil is somewhere between $5 to $6 a barrel right now. So that means to convert from raw material to finished product without including transportation of the product out of the refinery, the processing cost is 10% of the cost. So yes, there are margins there. And the processing cost is more when the crude is not as good quality. But then the incoming crude has to be cheaper. Otherwise, why would I process it? So refining companies do make money, but when the oil price goes high, their margins become very low, sometimes become negative. So the more efficient refiners continue to make money. And so it's all about managing cost and efficiency. Upstream companies make more money in general than downstream companies. They also have they need to have slightly different, well, not slightly different, but they need to have slightly different culture. So upstream companies, even at the senior most levels, it's all about taking risk. It's all about going to unknown places, investing millions in a wildcat well or an exploratory well, not knowing what you will get, taking geopolitical risks of going into countries where there may be corruption, there may be, all kinds of things. There's military rule, there's all kinds of stuff happening. You also have to be mindful of your reputation when you go to these countries, because there may be forced labor, aka slave labor, other human rights violations. So if you want to be selling fuel to your European Union, you cannot besmirch your reputation by being associated with, blood mining or slave trade or whatever. So there are lots of considerations that go in there. But on the whole, upstream companies are risk takers. They will go to, that's how they grow. They find reserves by taking risks. Downstream, by its inherent nature, you cannot be a risk taker. You don't wake up Monday and say, "Chalo kal refinery में जाके इसको ऐसे बदल के देखते हैं क्या होता है." I mean, you don't. So the mindset of at the senior most levels and the culture in the companies tends to be a little different. And so integrated companies that have both upstream and downstream, they have to manage. They have to have very different management sort of structures and populate them with the right kind of people. And going back to Saurabh's question about shale exploration, one of the reasons shale exploration took off in the US there were a lot of entrepreneurial people. I mean, George Mitchell, who started shale fracking in Fort Worth, and Barnett Shale in Fort Worth and in Oklahoma. I mean, he was a risk taker. You put in millions into a well and you get nothing, and you put millions into another well and you try fracking and you try something, and he kept trying till he succeeded, till he was able to produce gas, and then all of a sudden there's a new industry. So so the lifting cost, which is the cost of producing a barrel of oil to the surface, which includes all the costs that have gone until that time, the exploration, the drilling of the wells, the development of the field, everything to get to producing wells. That lifting cost is very small in some places which are prolific producers. A single well produces at such a rate that the lifting cost is single digits in dollars. So if you can, your marginal cost of producing a barrel, let's say, is $8, and you can sell it for $70, wow. And then there are places where the lifting cost, marginal cost for every additional barrel is $70, $60, $45. And then you don't produce when the oil price drops. You just close your wells. So again, this goes back to Saurabh's question, that in between shale oil production had stopped. What's happened to all those wells? Well, some of them have come back. Some of them are called drilled but not completed. So you drill the well, but you're not put it in production. So it's a semi-finished tap. You can very quickly complete it and within a month put it on production. But you've drilled it, something is there, and you've just closed it.
And how much has the industry evolved in the sense that it's they have to make a lot of drills to figure out whether there's anything there, or the technology is advanced where you can really predict ahead of time?
Technology has advanced, but okay, so here's an analogy, Srinivas. That's actually a very interesting or very good question. So here's an analogy which I think will help. So in in medicine, there is a process called fine needle aspiration cytology. It is literally so let's say that there's a suspicion that I have a malignant tumor in some part of my body. Fine needle aspiration cytology is you stick a fine needle there. It is invasive, but not as invasive as sort of a very proper biopsy. Doesn't involve surgery. If you can reach there, you reach there with a very, very fine needle, and aspiration is you just suck. So you suck a few cells or thousands of cells into the needle, and then take those cells to a lab or pathology lab to see if they are malignant or no. The problem is negative logic. So if you if you see malignant cells, it confirms there's malignancy. But if you don't see malignant cells, it does not confirm that there is no malignancy. It simply means you missed it. And I think the same thing is true of oil and gas exploration. When you look at a reservoir, a well is like a very, very, very fine needle. And non-invasive methods or surface methods can tell you probability of reservoirs and even shapes of reservoirs and sort of their aerial extent. But seismic can tell you that, but they don't tell you what's inside. So those rocks can be full of water. They can be full of an inert gas like nitrogen. They can be full of hydrocarbons and water mix. So the only way, with current technology, the only way to get there is an invasive process called drilling. And drilling may not hit the reservoir. So it's like that fine needle. You find oil, you know there's oil. You don't find oil, doesn't mean there's no oil. It just means you missed it. Your well was in the wrong place or the wrong angle or did not go deep enough or you didn't pay attention, you know, the presence of oil was masked by so many other unknowns. So any measurement you take in a well, now we have gone to the upstream side, any measurement you take in a well, the number of measurements is small. The number of unknowns is huge. Anything and everything is an unknown, you know. The chemical mineral composition of the grains, the shape of the grains, the sorting of the grains, you know, the binding chemical agents in between, the clays, the kind of clays, the hydration of clays, the kind of oil, the chemical composition, viscosity, I mean, temperature, pressure, yada, yada, yada. All these are so many unknowns. And then, you know, from M equations, you are trying to get to N unknowns, where N is much more, which means you have to make assumptions. And that's the art of exploration. The science is the measurements. The art is, am I making the right assumptions? I don't know these three things. Something is telling me that, you know, it's not very different from modern medicine. There's a lot of science, but then there's judgment on the part of the doctor eventually, connecting the dots, looking at patterns, recognizing things that you have seen in other patients. So it's still risky. And the cost of wells keeps going up because the wells are more and more in distant places. I mean, a land well in Permian today will probably, the cost of the well will be about $6 million. In the Gulf of Mexico, not in ultra deep water. In deep water, it's about $150 million. If you want to go Angola deep water, it's probably more than that. So those kinds of things.
So typically on land, oil is found at what depth, and in the seabed, how much below the seabed?
So typically you will not have oil very, very shallow near the surface. You do have some. I mean, Pennsylvania, the first well was 63 feet depth. You know, it was nothing. But most reservoirs are from the surface, you could say anywhere from 1,000 feet to 25,000 feet. Most of the wells that are drilled in the world today, except for deep water, which I'll come to, are probably 12,000 feet depth. So you're talking 3,000 meters, 3,500 meters. Most reservoirs there. Now, the deeper you go, the cost does not increase linearly. It increases non-linearly. In the sea, below the surface, I mean, from the subsurface part, that means below the water, it's about the same thing. You can find oil relatively shallow or fairly deep. The water depth is what makes a lot of difference. So, you know, you want to find oil 5,000 feet below the seabed, and the water itself is 20,000 feet, your well has become 25,000 feet right away. That kind of thing. Now yeah, and let's leave it there. So rarely you find oil oil or gas very close to the surface because there's over millennia, over so many years, generally there are some channels and it would have seeped, escaped, come to the surface, got oxidized, or just gone. Loss of pressure means the reservoir is no value. So usually you want to go below the surface aquifers, go to sort of consolidated rock, little hard rock, which can form a very effective cap on the reservoirs, not allowing oil and gas to migrate up. Though that is, in most cases, in my experience, in most parts of the world, that's about a few thousand feet below the surface. So I would say, 500 meters to 3,500 meters is sort of, it's a distribution, but that's most of the wells would fall somewhere there. Okay, we are at 2 hours. I think that's enough for the day. And I know there are still some questions in chat. I'll look at those, and if I can answer them, I will send an answer over email or okay.
Okay, then stop sharing and let us see each other. If
All right.
everyone can switch on their
Sure.
cameras.
Thanks, guys. I will jot down and see.
Yeah, that was wonderful.
No,
थोड़ा सा
thank you.
chemical engineering याद आ गया.
Ah. Okay. Guyana, Namibia, right?
I hope some of this will help Ponds with his, the home jobs, the handyman.
Ponch is going
Why
to start
pick
drilling
on-
in his own yard now.
Why pick on me here all the time?
Why? I hope you're going to drill there.
I
You
will
got
try.
a big enough
I will-
place, huh?
I will try. I mean, he did mention that you have to go down like 500 to 3,500 meters, right?
Yeah.
See,
It's not deep, man. You're retired.
No, so one of the things that you should be aware is there are a lot of restrictions on regulations. You have to make sure that you're not polluting or damaging the subsurface aquifers, which are a source of water, right? And so you have to drill past those. You have to stabilize your well. You have to cement it in place. Make sure there are no leaks, no possibility of leaks, and only then can you drill deeper. So those kinds of restrictions are there. And then when you abandon wells, there are, in most places, there are very strict guidelines how you have to abandon a well, how many, how effectively you have to close it to make sure there is no path for anything to come to the surface, gas, water, oil, whatever. And there are lots of leaking oils in the US where everybody has just abandoned them, bankrupted, sold, walked away, and the stuff is just leaking methane or other such things into the air.
Yeah, and also they don't give you mineral rights. Even if you own the property, it doesn't mean that you have rights.
Yeah.
Well, I'm surprised to see that Bhuvan has not joined this talk. This was the one talk that he would have been expected to join.
Nothing about coal,
then he
right?
could have, huh?
It's not about coal.
Well, yeah, but hydrocarbons is close enough.
No, I think the one thing I hope I was able to share was that choice of energy sources, or even the mix of energy sources, it is not a trivial thing. And that's the reason why different jurisdictions end up with different solutions, what seem to make sense for them. I mean, you have to assume that people who are involved in these decision makings, they're being rational. Now, their drivers may be different. We all yell and scream about California. I mean, my plant or facility is based in California, and I know how many restrictions there are. But if you are a resident of California, man, that air is so clean. It's so clean. And so again, these are choices that you are making, and yes, there are costs associated with them, but they're not straightforward choices. I mean, again, there was a discussion on that WhatsApp group saying, windmill doesn't produce electricity during the day then there's no wind and it's absolutely useless. And why are we building windmills? Well, I mean, lots of people in lots of countries are building windmills, so there must be some rationale. And the rationale is probably that windmills don't contribute to pollution. I mean, they don't cause, contrary to what Donald Trump said, they don't cause cancer. And yeah, I mean, some birds die, yes, but some birds die, in coal plants or, I mean, I'm not being callous here. I'm just saying that they are different drivers, and it's a multi-functional sort of a, you're trying to solve for what's optimum for you at that time, which is not optimum for others and may not be optimum for you at a different time.
We don't have to argue with Bhuvan, particularly since he's not present.
Yeah, well, I'm not arguing. I'm just saying that some of the comments made, that coal is wonderful. Well, coal is wonderful in many respects. It's the cheapest source of energy on a per kilowatt basis, no doubt. But it's also the most highly polluting, and it's no surprise that the stuff that is cleaner is costlier.
Well, coal is wonderful for historical reasons, if nothing else. I mean, it's what kicked off the Industrial Revolution. It's what brought us to where we are today. No question about that.
Yeah, no question, and it's still power sourcing. I mean, so many coal-fired power plants are there. It's still contributing or 25% of sort of our energy needs globally. And anyway, okay. Thanks, guys. Some good questions. I jotted down a few. I jotted down a few, and if I can find answers, I will share that with everyone.
Okay, good.
Thanks a lot, Cap.
All right.
Thank you.
Bye, folks.
Bye,
Thanks. Bye. Good night.
Thanks,
Good night.
Rajiv.